Okay. So Krenbühl and Koltun used a particular choice for this pairwise potential. And in fact, they used a so-called fully connected CRF. So usually, we have been using sparse Markov random fields, and I've been going on for hours and hours to tell you about the beauty of specifying only local interactions to get interesting global behavior. So this would be, the usual MRF with fork connection. They've used a fully connected one. So each pixel is connected with every other one. I'm not going to show all the lines here. And so for each of these edges, I should show the pairwise factor. And it's a conditional random field because the strength of this interaction depends on the similarity in appearance between these different sites. And this is closely related to a, so in fact they consider, interaction strength in a fully connected CRF is a function of both the spatial distance between two locations and the appearance distance or dissimilarity. So if two sites have very similar appearance, then such a model will typically learn that we want to have the same label there. And so this is a sort of modulation that you've seen, but you can of course make this depend on more expressive features than just the gray value at a given pixel. And now such a fully connected CRF, it looks like inference in there should be very hard, which is maybe why people hadn't thought about this so much previously. But if this interaction modulation is of a Gaussian type, then this whole thing can be implemented efficiently. And this has a close relation to a low-level operator from image processing called bilateral filter. In bilateral filtering, we proceed as follows. I'm giving you an example of just a single row of an image. This would be space. And this would be appearance. Appearance, so space usually, is 2 or 3 dimensional. Appearance can have very many dimensions, but if we just take the gray value at each pixel, then appearance would be 1 dimensional. So if I take a single row from an image, then my pixels will be equidistant in space, and well, they can be whatever in appearance. So for example, here we apparently have an edge somewhere along this row in the image. And bilateral filtering now says that we convolve these locations with, for example, a Gaussian filter, a filter which has limited extent in the spatial domain and in the appearance domain. And if I do this, I will get something that looks a little blurry. So I'm showing you a density estimate here. I'm convolving these points with a Gaussian, like in a kernel density estimation. The resulting blobs are not necessarily Gaussian. And then I ask at each position in space, at which appearance do I have the greatest, density. So I can now, at each position in space, I can ask for that appearance which has the greatest density, and then as a result, I would obtain something like I'm showing here in red. And you see that this is smoother than the original noisy data, and the edge has been preserved. I have a sharp jump here. Good. So this is bilateral filtering, and this inference in fully connected CRFs essentially it's a glorified bilateral filtering. It's bilateral filtering with more of a theoretical justification. We can do one more thing. If you look at this equation, let me write it out. I said that we have this compatibility function mu here, but this depends only on L prime, so we can exchange the order of summations and get something like the following. We will have Zi of L and now I do first a summation over the labels L prime, and then I'm pulling out this compatibility function mu of L and L prime, and then there comes the other summation over all sides j other than I. Okay, I'm just writing psi here for shortness times Cj of L prime. Okay, so this is the update equation, and we will see in a moment how this can be done efficiently. Oh, I shouldn't have written psi here, but k, excuse me. Psi is what I wanted to replace by k times mu. Okay, sorry. So I have k of xi and xj. Okay, good. And this thing here for k Gaussian and for the dimensionality of x preferably less than 8 can be done efficiently. And this can be done efficiently on something called the Permutohedral lattice. And that sounds maybe fancier than it is. But it's a very nice piece of work, and I here have the video which explains this super succinctly.
We instead propose sampling the space at the vertices of a sparsely stored lattice we call the Permutohedral lattice. The Permutohedral lattice is...
So the picture that you just saw was the same picture that I had shown with the spatial dimension and the appearance dimension. And now they explain the Permutohedral lattice. It is
by projecting a high-dimensional regular grid onto the subspace in which coordinates some.
Okay, so if you... Oh, no. No, I've changed the time. Excuse me. So...
The Permutohedral lattice. The Permutohedral lattice is formed by projecting a high-dimensional regular grid onto the subspace in which coordinates some.
So if you take just a Cartesian three-dimensional lattice, and if you look along the vector 1, 1, 1, then this cubic lattice looks like this when you see a two-dimensional hexagonal lattice. And the hexagonal lattice or honeycomb lattice, well, it's of course much better. This is the reason why bees build hexagonal honeycombs and not Cartesian square honeycombs, because you need less building material. So you have a smaller surface area per cell. So there are a number of criteria for what makes a good lattice. Its covering density or its packing density, so how closely can you pack spheres, or its second moment. And in all of these, the hexagonal lattice is better than the square lattice in 2 dimensions. In 3 dimensions, you have 2 generalizations of the hexagonal lattice. There's the face-centered and the body-centered cubic lattice. They are Fourier transform of each other. And in some dimensions, these dual lattices coincide, and in other dimensions, like in 3 dimensions, they differ. But they always are, so all these so-called root lattices are much, much better than the square lattice. Okay, so here they use this root lattice, which they call the Permutohedral lattice, which here looks hexagonal.
It tessellates that subspace with uniform simplices. So for splatting values into the lattice, we can use simple barycentric interpolation. For a d-dimensional lattice, barycentric interpolation touches d+1 lattice points, which is exponentially cheaper than using a grid and does not require any complex randomized tree queries, as with the KD tree. For blurring, we use it.
So, if you compare this to the picture I just showed, the picture up there, I had these original points where they had their coordinates. And they now do not retain these original coordinates, but they approximate them by barycentric interpolation. So we have this hexagonal lattice on top. And so each point, if I show here corners of this hexagonal lattice, each point we first find out in which lattice cell it is, and then we represent the single point here by 3 points sitting on the 3 adjacent vertices. This is called splatting, and this is what has happened here to our one-dimensional signal. Okay, now comes this Gaussian filtering, and the thing is, you know, if you look at the lattice here, it has 3 principal directions. In their video, these are blue. And it is, in general, not easy to define separable filters on these root lattices, but the Gaussian filter is an exception. Yeah? So if I now do a one-dimensional Gaussian filtering along each of these 3 directions, these are cheap one-dimensional operations, but taken together, they approximate a proper Gaussian pretty well. The approximation is not perfect, yeah? So a real Gaussian would be perfectly isotropic, and if we look at this approximation, what it does is it gives us a Gaussian which has, if we look closely, has a little bit of a hexagonal bias, but the bias is not too bad. Okay, so this is the blurring operation.
Conventional separable filter, and for slicing, we can reuse the barycentric weights already computed during splatting.
And now after this one-dimensional, after these one-dimensional blurs, the numbers that we found here at these vertices, they will have changed. And then we can, at each position in space afterwards, query for the position of maximum density. So this is called slicing in their language. And this is a very nice paper by Adams. And they have studied in detail in which regimes this is more efficient than alternative approaches that they and others have been working on before. And like I said, dimensions up to 8, this is a very efficient thing to do. Okay, so the merit of Krähenbühl and Koltun was to understand that mean field approximation could be useful, and that this message passing with the Gaussian potentials can be done efficiently using this method from Adams, and they've put it all together in a very nice system. Good, so this is the inference scheme, and now if you look at the update equations, this update equation, this can again be done for a given number of steps. Each step is again, I've forgotten the exponential here, each step is again differentiable, and that means we use the same basic idea as before with belief propagation, namely we unroll a fixed number of mean field iterations as a feed-forward neural network. And then do backpropagation through this network. So to summarize all of the above, applying iterations of either belief propagation or mean field and then predicting marginals from these, and finally loss, are all differentiable operations. So that we can, in principle, just use automatic differentiation to do backpropagation through that. And this is now a quote from the Justin Domke paper that I've referenced above. Questions from you? So all of this has been for categorical variables. What if Z is continuous? And what if the energy is quadratic in Z? Does it ring any bells? Have you seen this before? So if I write it, you may remember. So if I say that the energy of Z is Z transpose, this can or cannot depend on the input, Z plus some vector. Do you remember this?
Intrinsic.
Yep. So a Gaussian conditional Markov random field or an intrinsic random field is where we had seen this form. And there at the time, we had even seen how to learn these things. So we discussed loss-based learning of Gaussian conditional Markov random fields. And the learning problem was formulated, that's the same thing that we wrote down today. And we saw that it can be solved exactly by solving a linear system of equations. And the most difficult thing was to see how to propagate gradient through this matrix inversion. And this is where I invoked the matrix cookbook to look up this formula to see how we need to change the parameters so as to change the solution in a desired direction. And the formulas are given here. Okay. And I mentioned at the time the opnet as a small extension. The opnet also allows us, so opnet was a paper which also allows to impose constraints in addition. For example, AX Z should be larger than like this. So we have different choices of how we do the minimization. We can either solve a sparse system of linear equations, and then the formula needed to send gradient through this, we saw them in lecture 5. Or we could also just do gradient descent on this quadratic form. Or if you prefer, we could do Gauss-Seidel iterations here. Or this is a form of Gaussian belief propagation. In which case, we again get a simple iterative algorithm, and we can unroll this into a neural network as we've done earlier today. And the merit of the opnet paper is to show how to also do this if you have constraints in addition. They use a dense solver which maps well to the GPU, but would not allow to solve, problems on the scale of images. So this is still a topic of ongoing research interest. And in fact, Lorenzo Cerrone, master student in our lab, he is currently showing how to do that efficiently. So how to train a combination of neural network plus a Gaussian conditional random field, in his case a random walker, on top, and how to train that jointly. Okay, that's all I want to say about the continuous case. And before going to a completely different algorithm, there's a chance to ask questions if you have any. So bottom line is, after this hour, we know if we have a neural network plus a simple MRF looking like this, what we can do. If Z is discrete, we could either use loopy belief propagation or mean field iterations. If it's a Gaussian random field, we can use these matrix inversion formula, solving sparse systems of linear equations in there. Or we can also do it in terms of message passing. And you've seen in these examples and in the numbers, these accuracy numbers that I gave, this is actually worthwhile doing so. Okay, and you see when I start saying that people work on this in master's thesis and so on, you see that this is moving closer to my research interests. And as a last thing for today, I want to talk about something that we published recently at the last ICCV. And I'm recycling slides here that I showed elsewhere. This is the work of Steffen Wolf, who's a PhD student in the group, Lukas Schott, who wrote his master's thesis, Ulrich Kötte and myself. And we here looked at a seeded segmentation algorithm. Before diving into the algorithm, I want to show you what problem we've been using this on. This is beautiful data from Davi Bock. This is a tiny excerpt of a mouse brain, and Davi Bock has built a fantastic instrument with which to acquire images that are a few 100,000 pixels times a few 100,000 pixels in X and Y, and then many thousand slices in Z. This is mouse brain, but he has actually acquired the first fly brain at a resolution which would allow to trace all the processes in there, which us and others are currently trying to do. So here I'm zooming in, and yes, you see it's pretty massive data. And so this is, really the very tiniest part of a mouse brain, and you still see a lot of complexity here. So we have all these neural processes, which you see here in cross-section. We have these darker things, which are mitochondria. The small circles here are vesicles holding neurotransmitter. There on the left is a synaptic cleft. Do I have a pen here? Let's see. Oops. Okay. There we have these things are vesicles holding neurotransmitter. There's a synaptic cleft. So this is a synapse. And there's this level of detail throughout the entire data, and we're trying to see where each and every one of these processes are going. And for this, of course, we need to go through Z. So here I'm going through Z, and you see that it's not perfectly contiguous, but it's feasible. So humans can trace this data with very high accuracy. It's just that they take lifetimes and lifetimes to do this. So it's not feasible to do it manually. And this is why many labs are working on automating this. And this is the canonical pipeline that has emerged. So we start from raw data. Here use a neural network to detect cell boundaries. Then try and group pixels that we're sure belong to one superpixel, and then group the superpixels into what hopefully are the correct segments. So the first and the third step are, so we use a deep neural network here. We use a lot of machine learning there. But until not long ago, this step of coarse graining in the middle was not learned. And then there were 2 papers in 2016 that proposed the first differentiable algorithms, so that the entire pipeline could be trained end-to-end rather than just the individual pieces alone. What I'm going to tell you about is then our version of how we do this. Our overall pipeline, by the way, is currently the world record holder in accuracy in this on this data set. So it's not quite human accuracy yet, but nearly. And of course, we hope that this will give a boost to the neurosciences when people understand how the brain is actually wired up. Even just the brain of a fly. It's a bit ridiculous to imagine that we don't even know how a fly is wired up, not to mention people. Okay, so here we're looking at a seeded algorithm, and we've picked the so-called Watershed, which is an old school algorithm. It's a 1970s algorithm, but we've done it because it has no shrinkage bias, unlike Markov random fields and such, and because it's super fast. So the Watershed algorithm, it defines an optimization problem, and this optimization problem can be solved very efficiently. I could write it as a probabilistic graphical model. I could give you an integer linear programming formulation, but the optimization problem has a beneficial structure called matroid structure, which makes it very, very easy to optimize. So like I write here, the greedy algorithm gives the optimal solution to this. This can be formulated as a minimum spanning tree problem. Seeded segmentation means that we have an image. In this case, my image here has 9 pixels. I have, just to illustrate the algorithm, I have introduced some edge weights here, where lower is better. And in seeded image segmentation, well, we have seeds. So it's, what this says is that I want 2 segments out where this pixel lies in one segment and that pixel lies in another segment. I introduce seed nodes, and I'm using a minimum spanning tree formulation here, which connects the seed nodes to a meta node. All of these extra artificial nodes have a 0 edge weight. And I now use Kruskal's algorithm for minimum spanning tree computation, which starts at an arbitrarily designated root node and now always adds the cheapest reachable edge, except if it would introduce a cycle, because then I would no longer have a spanning tree. Yeah? And I want a tree which is a cycle-free graph. So starting from the root node, this has 0 edge weight, so I can add it. I can add this one. This has 0 edge weight. I can add this one. I can add that one. And now I have a couple of edges to choose from. Yeah, like the weights here are 3, 4, and 5. And the weights here are 6, 7, 8. So the smallest of these is 3. Now a new edge has become reachable, which has a cost of only 2. This is the cheapest edge I have accessible, so I'm going to add it. Now I have new edges accessible with weights 1 and 11. 1 is the cheapest weight overall, so I'm adding this. And now the next one, next cheapest would be this one here. And the next cheapest one would be this one, but I cannot add it because this would induce a cycle, and I must not have cycles. Next cheapest one would have this one, but it would induce a cycle. I cannot do it, but I can add this one and this one. And at this point, I have spanned, I want a minimum spanning tree. Now I've spanned all the vertices, all the pixels in my image. Okay, and did you see? My spanning tree now induces a segmentation. Namely, I can now look at which pixels are connected to the green seed and which pixels are connected to the blue seed, and this gives me a segmentation of my image. Okay, and this formulation of the Watershed algorithm has been known for some time. Maya in 1994 was the first to propose it. Now the crucial observation here is that Kruskal's algorithm does not need to know all edge weights at the same time. It only needs to know the edge weights of those edges which are reachable, which are at the shore of our current graph. And this is what we want to capitalize on. Yeah? So we want to compute costs on the fly, not from the beginning, as you've seen in this example, but we want to compute the edge costs that reflect some of the image properties only when they're truly needed, just in time. And secondly, we want to be able to train the whole thing. And training the whole thing, the point here is that I mentioned this pipeline here, that the first step was learnable, the last step was learnable, but the in-between was not learnable. And we want to, learn it rather than handcraft it, and especially we want to make the whole thing end-to-end trainable. Now, we use this idea to unroll this into a neural network. So we keep the structure of the basic algorithm. It was not Kruskal, it was Prim's algorithm. Excuse me. So we keep the structure of the algorithm, but we use a neural network here shown, symbolically in magenta, to estimate the costs of the edges which have become newly reachable. And so this can be written as a deep network, which can be trained from ground truth data using backpropagation. And then the result is that you can learn desirable behavior. For example, from the data that David Bock provided, on the top you see the ground truth, the raw data, and then the ground truth. Then you see the best handcrafted watershed algorithm, and a cherry-picked example where this learned algorithm does better. But also in terms of numbers, if you do this on bigger data set, is a little bit better than the best learned algorithm. This was published at the last ICCV last fall, and I want to show you what this looks like. So the needles are the seeds, and this is how the algorithm explores the space. And we like to think, we don't know what it does because it's a deep network, but we know two things one thing we know for sure, namely that we get out a tree, because we have retained the structure of the basic algorithm. And we like to think that it imitates the human in the sense of doing the easy parts first and the hard parts later. Well, and the results, as I said, in numbers are actually very good. Now, having an algorithm which needs seeds is of course not satisfactory. So right now we're working on getting rid of the need for seeds. And this is again Steffen Wolf doing it, and it looks pretty good so far. Which brings me to the end of today's lecture. So the bottom line is that we have talked about how to jointly optimize a neural network plus a graphical model, either a grid-shaped conditional random field or the watershed that I showed last is a very special type of a graphical model. But you see that an important basic trick is to try and unroll this into a neural network and then do backpropagation through that. Next time we talk about reinforcement learning, and until then, have a good week.